What are we gonna
I'll be the local.
do? Okay,
And, maybe, yeah, you can sit there.
but where are you gonna sit?
There. No,
You can also just sit there then. Maybe. Yeah.
no, it's.
But where do you want me to sit? I can sit anywhere.
You can sit there
And just make sure that everything
Zoom,
is-
yeah, like you did last time.
Yes, but then Alexei is also online, right?
Yeah, but it's okay. But
I will just keep track.
yeah.
Okay.
So I think we can begin. So hello everybody, and welcome to the cryptanalysis, first cryptanalysis session. We're going to have 6 papers presented at the session, and the first paper is going to be increasing precision of division property by and Patrick Derbez is going to give the talk. So go ahead.
Can you point the camera a little bit higher so we can see your face?
Okay, thank you for the introduction. So I will not introduce what is division property, but somehow it's a tool to track the biggest monomials of iterated functions. So basically, to search for division property related properties, we look for division trails through iterated functions. And so you have to decompose your function, your target, into several layers. And each layer is a very small one, very small layer, like small S box or linear layer and or any binary operation, because you need to be able to compute the polynomial expression of any output bits and of any product of output bits. The problem of division property is that it does not really handle the XOR operation because it does not see any monomial cancellation through the composition of functions. So what we did in this work is all about increasing the precision of division property. So first, our idea was to handle larger functions, larger layers than previously. So we proposed a new algorithm to compute valid division property propagation for super S boxes and for big functions up to 16 bits. Okay, so basically this new algorithm takes as input a collection of k and big functions and output the propagation tables containing all the transitions which are valid for at least one of the functions. And I insist that this is not a weak key model, okay? Because in division property, you have an integral distinguisher if and only if there is no trail. So it works. So here you have the complexity of our new algorithm. And we successfully applied it to super S boxes of many ciphers. And it takes around 2 hours on a 128 core server. The second improvement we made in this paper is related to extended distinguisher. So basically, we know that division property is not linearly invariant. And so if you want to study a given cipher, you need to study it with all possible linear mappings at the end or the front of the cipher. And we started this work with Baptiste Lambert, and basically at this time we proposed to try all invertible matrices. But in this work, we found that we can reduce the number of possibilities of linear mappings to try. Okay, and basically, if you don't want to reduce the data complexity of integral distinguisher, you only have 2 to the n linear mapping to try in front of the cipher and 2 to the n linear mappings to try at the end of the cipher. And this combines well with the super S box techniques, and there are minimal pairs of mappings to try for, meaning that if there is no distinguishers for those pairs, there will be no distinguisher for any pairs. Okay. And the problem, so now we introduced all that. The problem was how to search for distinguishers. And the main problem is that So most models to search for the integral distinguishers are generic solvers, generic solvers, are SAT or MILP. And the problem is that describing the constraint so the constraints for describing the propagation table of super S boxes are too big. Okay, in the propagation table of super S boxes, there are like millions of constraints and of valid transitions, and describing it into a MILP model leads to very inefficient models. So that was recently solved by Udovenko, but in this paper, we choose another way. So we implemented an ad hoc tool to search for such distinguishers. So it's a basic tool based on a branch and bound approach, and it takes functions, so block ciphers, which are of this form. So each round or layer are decomposed into 4 16 to 16-bit functions, okay, which may depend on the key, and then enable permutation. Okay, so if each round has this form, it's okay. And the function f do not need to be the same for each round. Okay, so this is very generic. We applied this tool against 3 ciphers, so against Midori 64, Skinny 64, and height, and we found many new integral distinguishers against those ciphers. So you have all the results here. And in particular, we also found many integral distinguishers with low data complexity, okay, by setting the input of many super S boxes to constant. Okay. So that's all for in 5 minutes. So you have all the code of our tool is available here. It's very easy to use. And if you want, if you have any question about this tool, I can help you with it. Okay. Thank you for your attention.
Thanks a lot, Patrick. Any question? Maybe one quick question. We have time. Okay, so let's thank Patrick again. I believe the next talk will be presented online. And so do you hear me on Zoom?
Yes.
Okay, so it's going to be on the relations between different methods of degree evaluation, and it's going to be given by Seu Chen. So please go ahead.
Thank you. Hello, everyone. I'm Seu Chen. The title of this report is on relationships between different methods for degree evaluation. This is joint work with Zhejun Xiang, Qiang Yongzhen, and Xiaoshao Zhang. Our report is composed of 4 parts. First, we will give a brief introduction on the background of our work, and we then discuss the degree evaluation of SPN and NFSR-based ciphers in part 2 and part 3. Finally, we will conclude our work in part 4. The outputs of symmetric ciphers can be regarded as point functions over their input variables. So if cipher exhibits low algebraic degree, some distinguishing or recovery tasks can be achieved. So it's very important to estimate the tag bounds on the algebraic degree. There are 4 effective long-tail methods for degree evaluation. First, for the SPN ciphers, there are 2 formula-based bounds. One is proposed by Bora and Candide. We call it BC bounds. Another one is proposed by Khalid. We call it Khalid bounds. This example shows the effectiveness of the 2 bounds. For NFSR-based ciphers, Liu proposed a method called numeric mapping, and especially for trivium-like ciphers, efficient algorithm was given in this paper. Last one is division property. In the application to search for integral distinguisher, we usually fix the input dp and to minimize the output dp. When evaluating the algebraic degree, it's a reserve process. That is, we fix the output dp and to maximize the input dp. And the the maximum of the input dp can be regarded as the upper bound on the algebraic degree. Let us first focus on the SPN ciphers. From the previous introduction, we know that BDP method is the whole process, but the two bounds is the iterative process. So we cannot compare them straightforwardly. So we have to construct a bridge to link them. Okay, this is our bridge. It's a loop bound on the degree of composite function of G and Ft. And the T is a flexible integer. So in the case of T being 1, we can have the two conclusions. They indicate that our loop bound is more accurate than BC bound and Khalid bound. This proofs of the two conclusions we omit here. If you are interested in them, you can refer to our paper. So let us focus on the bit-based division property with two bounds. This is our bridge. By fixing the value of the different value of T and considering different type of division property, we have three models. The first models, we consider the bit-based division property, and the G is an identical function. That is the algebraic degree of G is actually 1, and we set T2R. In model 2, we consider word-based division property, and in model 3, we consider word-based division property, and we set T21. In this case, the function G is always varying with the round increasing. So literally, BDP method is equivalent to the model 1, and from the previous analysis, we know the model 3 is more accurate than the two bounds. Moreover, BDP is a more accurate division property type than WBDP, and the model 2 considers the influence of linear line on the division property propagation. So the model 1 is more accurate than model 2, and model 2 is more accurate than model 3. As a result, we have this conclusion is that the BDP method is more accurate than the two bounds. Let us consider the NFSR-based ciphers. Assuming that there is a simplified stream cipher based on an n-bit NFSR, this is the update process of the interstate, and the function G is the update function, and F is the output function. This is the simplified process of encryption. We first propose two bounds on the DP degrees of AND and the XOR operations as illustrated in proposition 4 and proposition 5. Proposition 4 indicates that for a monomial, its DP degrees is no more than the sum of the DP degrees of the involved states, and proposition 5 indicates that for a polynomial, its DP degree is the maximum of the DP degrees of the constant monomials. Based on the two propositions, we have this conclusion, is that for any state bit at any clock t, its DP degree is more accurate than its numerator degree. Note that S0 is the initial state, so the both of the dp degree and the numerator degree are equal to the exact degree. At clock 1, the state Sn, we can get this form from the proposition 5, and this can be rewritten as
Sorry,
this
can you
form.
please try to wrap up? We're running out of time.
Oh, okay. So we can have this form from proposition 4. So finally, we have for the state Sn at clock 1, we have its dp degree is more accurate than the numerator degree. We omit the experiment results. So, so in this work, we gave arguments on the relationships between different methods for algebraic degree evaluation, and we conclude that division property is the most one from the accuracy perspective. In fact, there are two methods to compute the exact degrees. They are monomial prediction and the 3 subset division property, but you have to explore some special optimization strategies because both of them have to enumerate what the truth from the input propagating to the output. So if you only want to get the overview on the degree of the cipher, the 2 subset division property will be the best choice. That's all my report. Thank you.
Thank you very much. So I think we don't have time for questions, so we'll move to the next talk.
Okay, thank you. Sorry.
Oh, it's
We have to close this one.
no,
Close.
what do you mean by close? Oh, you mean close the file?
Yes.
Oh, okay.
So we can go back to Zoom.
Yes, it's no,
No.
wait. It's the influence.
Okay, we don't see it anymore,
We
right?
don't see it. Yeah.
Okay, so we'll just okay.
No.
This
okay.
one, right?
Yeah.
Okay, then we'll go back to the Zoom. Share screen.
And no full moment. Okay, so the next talk is going to be influence of linear degree on the algebraic degree of SP networks, and it's going to be given by Reinhard Luftanger. So please go ahead. Yeah.
All right, yeah, thanks for the introduction. So yeah, this is a joint work together with Carlos from Royal Holloway University in London, Lorenzo and Aldo from the Radboud University in the Netherlands, and Kristen and Markus from our research group at Graz University of Technology. In our work, we're studying the algebraic degree in substitution permutation networks. But why is this important at all? We have seen a slide in the previous talk, but I may repeat it anyway. So it is the algebraic degree that determines the cost of several types of algebraic cryptanalysis. I'm speaking here of interpolation cryptanalysis, higher order differentials, and to some extent also of solving systems of polynomial equations over F2. The problem is, in practice, we don't know the exact algebraic degree of full-scale cryptographic permutations. So this is the reason why we establish upper bounds on the algebraic degree. In our work, we present and prove a new upper bound on the algebraic degree in SPNs. And what is special about our bound is, besides the degree of the nonlinear layer, it also considers the degree of the linear layer for its estimate. And I say special because other state-of-the-art bounds do not use this property for their estimate. Yeah, most notably, our bound is considerably tighter for low-degree round functions with large S-boxes. But on the contrary, it may not improve state-of-the-art bounds for small S-boxes or high-degree round functions. And speaking of the actual comparison, so we compare our bound with the bound by Christina Bura and Cantor and Christophe de Canière, which is arguably the best theoretic upper bound in the literature. And yeah, I will refer to this bound as the BCD bound. So if you'd ask me about a visualization of our results, then I'd probably answer with this slide. So the diagram on this slide shows several bounds on the algebraic degree for an SPN here with 8 words, and each word is operating over F2 to the 33. The S-box function here is the cubic function, and the degree of the linear layer here ranges from 1 to 8. So now this horizontal black dashed line shows the maximum algebraic degree, whereas the blue line, I don't know if you can see the colors, so the leftmost graph depicts the BCD bound. For the other lines, they depict our bound on the algebraic degree for various degrees of the linear layer. Maybe 2 important points to note here. So first of all, you can see that there are potentially 2 phases of algebraic degree growth. There's a phase of exponential growth for the beginning number of rounds, and followed by a phase of linear growth for the remaining number of rounds. Our bound helps to quantify these 2 phases. So for example, you can observe the phase of linear growth is all the more prominent the lower the degree of the linear layer is. The red line, so the rightmost graph, shows a linear layer with degree 1, and in this diagram exhibits the phase of the longest phase of linear growth. The second point is, you may observe there's a gradual shift of emphasis from linear growth to exponential growth as the degree of the linear layer increases. So having an upper bound on the algebraic degree gives you a lower bound on the number of rounds to reach, for example, maximum algebraic degree. This table here shows the number of rounds to reach maximum algebraic degree derived from our bound and the BCD bounds, and also shows some practical results. The SPN here again uses the cubic function as S-box function, and the linear layer in this example is defined as a multiplication with a matrix, with a certain MDS matrix. Now, the important point here is you can see as the size of the S-box increases, also the advantage of our bound over the BCD bound increases. You can observe this as you move down in this table. Yeah, that's about it. So if you're interested in this work or it seems relevant to you, feel free to have a look at the online video, also to have an in-person discussion during our stay here in Athens. Thanks.
Any questions?
I have a question. Can I ask?
Yes, of course.
Yes. So thanks you, Reinhard, for the talk. In the full talk, you mentioned that structure of the linear layer is a potential for improving the bounds. Do you have some examples in mind where the structure of the linear layer can help?
So our bound does not incorporate the concrete structure of the linear layer. It's just the degree of the linear layer that we incorporate into our bound. Of course, so we expect that using the concrete structure of the linear layer, more can be said and potentially more accurate bound can be derived. But for our bounds, at least for now, it does not incorporate the structure.
Okay, thank you.
Any other questions?
In practice, does the degree of the linear layer depend on some particular property of this layer, or do you have to compute it?
Yes, yeah, you would just compute, sorry.
Repeat the
Yeah,
question.
thanks, yeah. So the question was about the degree of the linear layer, if it depends on some properties or if you would just compute it. And you would just compute the degree of the linear layer, see what it is, and then apply our bounds. Yeah.
Okay, great. Thanks a lot for the talk, and let's thank Reinhard again. Oh, Christina, maybe you can. Yeah.
So we'll go open next one. Legendre. Okay. So we'll go back to Zoom and then share the Legendre. Okay. So have to close.
Yeah,
Open menu
I
and,
understand, but I'm not doing
That's fine.
Okay, so the next talk will be on the Legendre symbol of modulo 2 operator in symmetric schemes over FPN, and the speaker will be Lorenzo Grassi. So go ahead.
Thank you very much for the introduction. So the motivation of this work is about the recent progress in applications like multi-party computation, fully-morphic encryption, and zero knowledge. And this application needs some symmetric crypto over prime fields. So in this paper, we consider two problems. We look for a new permutation over FP that are based on the Legendre symbol or the modulo 2 operator. And we consider the security of a symmetric primitive that is instantiated with some of these nonlinear functions. And in particular, we propose a concrete attack on the sponge hash function, Crandall. So let me just recall what the Legendre symbol is. So the Legendre symbol is a function that maps FP to -1, 0, or 1. So the output is 0 if the input is 0, and the output is 1 if the input is a quadratic receiver, and -1 otherwise. These are some examples of functions that are based on the Legendre symbol and that are invertible. So the first one is takes x and return x to the power of t times alpha plus the Legendre symbol of x. And this function is invertible if t is co-prime with p-1 and if alpha square minus 1 is a quadratic receiver. For example, alpha equals 0 satisfies this assumption if p is equal to 1 modulo 5. Now we can also fix alpha equals 0 and we can get a permutation, but we have to change a bit the assumption. So in this case, this function x to the power of t times the Legendre symbol of x is a permutation if the GCD between d plus p-1 alpha and p-1 are co-prime. And this is the function that is used in the Grandai hash function. And another example of function based on the Legendre symbol and it is invertible is this power map, where the exponent depends on the Legendre symbol of the input. So you can find other invertible function based on the Legendre symbol in the paper. Let's just have a look to some function based on the modulo 2 operator. So we all know that the square map is not invertible, but we can slightly modify the square map in order to get an invertible function. For example, in this case, we have that the function that takes an input x and return x squared if x is equal to 0 modulo 2, and it returns alpha times s squared if x is equal to 1 modulo 2, is a permutation if the Legendre symbol of alpha is equal to -1. Again, an example, we can fix alpha equal -1, and this assumption is satisfied if p is equal to 3 modulo 4. And in this case, I would like to observe that we don't have to compute the modulo 2 operation. We can just have to compute the exponentiation. And finally, we can also slightly modify this function. And we can get an invertible function like this, so -1 to the power of x squared times x to the power of t, where this function is invertible if p and p-1 are co-prime. So in the paper, we study the statistical and the algebraic properties of all these functions. I'm not going into the details, so you can find this table in the paper. To summarize, they all have good statistical and algebraic properties. So what happens now if we instantiate a symmetric primitive with one of these functions? Well, they have good algebraic and statistical properties, but they have a problem. And the problem is that they take a large set in input and they just return a small set in output. For example, just 2 or 3 output. So what is the idea? Well, we can break a primitive instantiated with one of these functions using this approach. We can fix all possible Legendre symbols or the modulo 2 functions, and then we construct the system of equations that describe the primitive. Then we solve the system using, for example, root finding techniques, factorization, Krupna basis, whatever you like. And finally, we can check if the found solution satisfies the Legendre symbol that we fixed in the first step. If this is the case, we found a solution. If not, we just repeat. A concrete example, here we have Grendel. So Grendel is a sponge function, and this is the permutation that instantiates Grendel. So we have constant addition, multiplication with MDS matrix, and S-box, where the S-box is just x to the power of t times the Legendre function of x. We use this approach, and here we can find the comparison between the number of rounds of Grendel for different values of the degree t and the size of the permutation, the number of rounds that we are able to break, and the number of rounds that we recommend based on our attack and other consideration made in the paper. And you can see that in some cases, we can break many more rounds than the one proposed in the Grendel paper. So that's it from my side. So summary, we can use the Legendre symbol or the modulo 2 operator to set up permutation of the FP. We have to be very careful when doing this. So possible attacks are possible. So sorry, attacks are possible. And the open problem is to understand if functions that are associated with the Legendre symbol or the modulo 2 operator are efficient in these kind of applications. Thank you very much for your attention.
Any questions to Lorenzo? Okay, if there are no questions, then let's thank the speaker again. So the next talk will be presented online. It's going to be on automated search oriented to key recovery on ciphers with the linear key schedule. And Lynn Guay Quinn is going to give the talk. So go ahead.
Thank you. This is a joint work with Xiaoyang Dong, Xiaoyun Wang, Keting Jia, and Yunwen Liu. Differential attack is one of the most successful cryptanalysis techniques. In distinguishing attack, good differentials are those covering the highest number of rounds or with the maximized probability. For key recovery attack, attacker needs to append several extra rounds EB and EF to recover the keys. A good K recovery attack often requires a comprehensive trade-off between the K recovery and the differential. In this talk, we try to maximize the number of attacked rounds with data and time complexity lower than that of the exhaustive search. The constraints include the probability of the distinguisher, the active bits of the input, output, and the K bits need to be guessed in the extended rounds. Boomerang attack is proposed by Wenger. Two short differentials are combined into a longer boomerang. The boomerang attack can be converted into chosen plain text attack, known as the amplified boomerang attack or rectangle attack. We analyze the detailed factors of Zhao et al.'s rectangle framework for block ciphers with linear key schedule and gave a new automatic MILP model. The model is applied to Skinny, which follows an ESPN structure and a take key framework. The family of Skinny has 6 main versions. There have been several works discussed the automatic searching model of Skinny. Our new model is mainly based on the latest 2 works by Hadipo et al. And Dallon et al. We present an extended model to searching for the entire NB plus ND plus NF rounds of an attack. Our target is to maximize the total attacked rounds. In practical programming, we take the rounds as the parameters to input the model, and the target is the time complexity. The time complexity of the rectangle attack is highly related to the number of guessed Ks in EB, since the matrix in the MC operation is not an MDS matrix. The subtopics involved in the partial encryption and decryption are different. So we model MB from 2 aspects. In phase 1, in order to compute the active cells in Y3, we need to know the cells marked by red dots in X3. Then the cells need to be known in Z2 can be deduced through the linear diffusion. In phase 2, we compute Y3 bar and then deduce delta X3 and delta Y2. Then the calculation from P2 to Y2 is similar to phase 1. So in our programming of the new model, we integrate the about 2 phase. The cells need to be known in ZR, can be deduced from XR plus 1 through the linear diffusion as phase 1. Then the cells need to be known in XR involve 2 types, the active cells in phase 2 and the cells need to be known in ZR. The objective is the time complexity, and we add the variables on behalf of different parameters to the function. Because different parameters have different coefficients, we give them different weights. With our new MILP model, we search for more proper truncated differentials for K recovery attack, then use the CP model to get the actual differential. In the table, we compare the related take key boomerang distinguishers for Skinny. Use the new distinguishers, we give improved K recovery attacks. For Skinny 62192, we extending 4 rounds EB and 4 rounds EF. We attack to 30 rounds. In data collection, we generate quartets satisfying the input-output differences. Then the K recovery process is just a guess and filter process. We summarize the cryptanalytic results on Skinny in related to key setting. For 3 reasons of Skinny, our results cover 1 more round than the best previous results. The new model is also applied to Fork Skinny, which is designed under the Fork AE framework. The primitive is based on Skinny, previous analysis of skinning can be directly applied to fork skinning. But as pointed out by Barrett et al., encryption from M to C1 use a slightly different turnkey schedule, leading to better analysis. For example, in some cases, there can have 6 consecutive inactive round turkeys. We add those constraints to the automatic model of skinning. So for fork skinning 1 to 8, 2, 5, 6, we select a new 21 round related turkey rectangle distinguisher and give improved attacks with different turkey sizes. Our results for fork skinning cover 1 to 2 more rounds than the best previous work. Thanks for your attention.
Thank you very much. Are there any questions? Okay, if there are no questions, then we can move on to the next speaker, which will also present online. Okay, so the next talk will be improved attack on S-list permutation and tight bound on limited birthday distinguishers. It's going to be given by Yu Sasaki. So Yu, go ahead and good luck.
Okay, thank you for the introduction. So, so this is a joint work with Akinori Yamada from NTT and Ariane Presencia from India. So as the title suggests, that this is a combination of dedicated attacks and use of generated attacks. So the dedicated attacks, the target is SLI-SCP. This is a cryptographic computation designed to use for the SPON framework to build IPA. The original SLI-SCP was proposed at SAC 2017, and then later its light version was presented. And in the NIST light cryptographic competition, 2 schemes, SPIX and SPARC, are based on SLI-SCP Lite. And right at the time of the publication, SPIX and NIST were in the second stage, and SPIX and SPARC were the second contenders. Okay, so the figure below shows the computation structure. And for SLI-SCP, it consists of 18 steps, and each step adapts the 4-branch generalized basic structure. And the F function is reduced random where the key is replaced with some constant. And for SLI-SCP Lite, the position of the SMEC function is moved. And so it looks like MIST structure. So 2 rounds can be computed in parallel. Okay, so this is the overview. So for the first part, we present improved cryptanalysis. And the previous test attacks on SLI-SCP were limited birthday signatures by rebound attacks. So rebound attacks consist of one phase and that phase, and we improved both phases to achieve some reduced complexity or more steps. So depending on the permutation size, the which of the original version or the light version we're attacking. And this is the first third-party analysis on SLI-SCP Lite. Yeah, so this is the dedicated attack results. And so to be a valid attack, so we must compare the dedicated attack complexity with the generic attack complexity. So ideally, lower bound of the generic attack. And this is the second topic. So, however, the lower bound of the limited birthday distinctions or permutations are not known. the problem can be defined for the function, and in case of function, the lower bound is known, but it was open for the partition. So in the previous distinction attacks, they made a conjecture for the best attacks, generic attacks. So it uses the upper bound to assume that any attack faster than the best upper bound is a valid attack. So this is a conjecture, and we tacked the problem in this talk, in this research. Well, so our approach is simple in approach-wise. So we define the game, and I define the best strategy to win the game, and simply evaluate the number of queries to win the game. But the iteration is complicated. But in the end, we obtain the lower bound, and it matches the conjecture for the best generic attack. So all attacks based on the conjecture is actually valid. Okay, so this is a one-page slide for the proof results. So limited basket distinctions first specify pros of the set of input difference and pros of the set of difference. And the goal is to find the two texts xy and x-y dash such that the difference and that difference are in the pre-specified set. And the previous attack was given by Jippe and Kulan. And best attack strategy depends on the size of the input and the space. And we proved the following lower bound. And we have coefficient 1/4 at the beginning, but basically it matches the previous test attack up to the constant factor. Okay, so this is a one-page slide for the reason for the cryptanalysis improvement. The previous attack is a redundant attack, and we use the 15-step record. And in the redundant attack, attacker first choose the state values to satisfy different transition of the middle part. And in the previous part, the inbound phase covers 3 steps, and there's 12 steps are satisfied probabilistically. But in this research, we found that by carefully choosing the values in appropriate order, inbound phase can cover 1 more steps without increasing the complexity. So, I mean, this is just the beginning of the analysis, but basically the fundamental idea to improve the attack. Okay, so the research contains 2 aspects, and for the cryptanalysis, and the number of attack steps reached 16 now. But I have to say that the attack is only for the underlying computation. So there is no impact to the security of the space in the Spark as APD. And we also show the new lower bound, and which is tied to the best attack up to the constant factor. Yeah, thank you very much.
Thank you very much. So any questions for you? Okay, if there are no more questions, then let's thank the speaker and all the speakers of the session. So now we will go to lunch until 2:15, and then we will resume with the in-person only workshop. So see you. And of course, for the rest of the participants, the conference will resume tomorrow. So it will be earlier. It will start from 9 o'clock. Okay, that's the first session. 9 o'clock local time, of course. So you should calculate.